folks. Today we're going to talk about parallelograms. In the last set of notes, you talked about angles of polygons, so you kind of got an introduction into the polygon unit. That definition of a polygon, and this is just verbatim from the last set of notes, is a polygon is a closed plane figure, so a two-dimensional figure, formed by three or more segments, such that each segment intersects exactly two other segments, and only at their endpoints. And no two segments with common endpoints are collinear, so we don't have two sides that kind of make one long line segment. That doesn't happen here. So today we're going to extend our knowledge of polygons in general to talk about parallelograms. The definition at the top, a quadrilateral with two pairs of parallel sides is a parallelogram. And a parallelogram is a polygon. So it's a quadrilateral. Let's break this down. Quadrilateral, what does quad mean? Four. Lateral, kind of lines, so four sides. With two pairs of parallel sides, so that means that we've got opposite sides as parallel to each other. Now to write the name parallelogram, you can either write out parallelogram in letters, or you can use the symbol, which is a parallelogram. So we've got several different properties of parallelograms that we want to discuss. There are a lot of different theorems that are here, and so what we want to do is we want to go through them. We want to talk about all the cool properties of parallelograms. We want to shorten all of the theorems that we talk about so that it's easy to kind of write them as an explanation later on in our problems. And we want to make some conclusions about the theorems that are being used. So the first one says, if a quadrilateral is a parallelogram, so if a four-sided polygon is a parallelogram, opposite sides are parallel, then its opposite sides are also going to be congruent. Meaning, if I have quadrilateral ABCD, and let's say this is a parallelogram, so I know this because it tells me that this is a parallelogram, then I can say the opposite sides are congruent to each other. So side AB and side DC are congruent to each other. Side AD and side BC are congruent to each other. So my conclusion over here, the opposite sides being congruent, would be that side AB is congruent to side CD or DC, however you want to say it, and is congruent to side BC. Remember that sides, if we're talking about like the actual line segments, those are figures, those are pictures, those would be congruent. We cannot say that the sides are equal. That does not make sense. Pictures cannot be equal. Figures cannot be equal. Sides cannot be equal. But the measure of those side lengths can be equal. But here we're talking about the actual pictures and figures, not the numbers. So let's move on to the shortened version of this theorem. So typically, we would say P implies Q, right? So for our conditional statement, if P, then Q. This is my conditional statement format. So here, the hypothesis was if a quadrilateral is a parallelogram. So we're going to abbreviate this with if parallelogram. Then, what was the conclusion? The opposite sides are congruent, right? So remember, this is an abbreviation to use in justifications later on. So opposite sides congruent. See how shortened that is? Makes it really easy to use it to justify things later on. Okay, next theorem. It says if a quadrilateral is a parallelogram, so again our picture is a quadrilateral and it's being told to us that it's a parallelogram as well, then its opposite angles, not sides but angles, are congruent. So quadrilateral ABCD is a parallelogram because they told us it was. And then we can make the conclusion that opposite angles are congruent. So angle A and angle C are congruent to each other. So angle A is congruent to angle C. Again, we're talking about the figures. We're not talking about their degree measurements. In the numbers, we're talking about the actual figures, so they're congruent to each other. And the other pair of angles that are opposite of each other are congruent to each other. So angle B and angle D are congruent to each other. Angle B is congruent to angle D. Does it matter which order I write these in? Absolutely not. But it is important that I have both of these claims here, that both pairs of opposite angles are congruent to each other. Also notice that in the picture, angles A and C have one arc mark, angles B and D have two arc marks. That's because angles A and C are congruent to each other, but they are not congruent necessarily to angles B and D. So make sure you have a different set of arc marks for that second pair of congruent opposite angles. So if I'm going to abbreviate this to use in my justifications later, I'm going to say if a quadrilateral is a parallelogram, so if parallelogram, then opposite angles are congruent. So I'm going to say opposite angles, that's the angle symbol, and then congruent. Even easier than the other one. All right, let's move on to the third property of parallelograms. It says if a quadrilateral is a parallelogram, then its consecutive, meaning one right after the other, then its consecutive angles are what? We've talked a lot about transversals and parallel lines, which we can kind of incorporate into these parallelogram pictures. But consecutive angles are typically what? Supplementary. So, again, the quadrilateral, it tells us that quadrilateral must be able to assume that its consecutive angles are supplementary. Angle A plus angle B, so one angle right after the other. Angle A plus angle B must equal, if they're supplementary, 180 degrees. Remember, you need to add on the units here. This is 180 degrees. We are measuring in degrees. The next set of consecutive angles would be angle B and angle C. So because they are consecutive and this is a parallelogram, then when I add those two measurements together, I should again get 180 degrees. Angle C and angle D, consecutive, one right after the other. If I add the measures, I end up with 180 degrees. And finally, angles D and A are consecutive, one right after the other. So if I add their measures, I should get 180 degrees as well. If I were going to shorten this property, I would say if a quadrilateral is a parallelogram, so if parallelogram, then consecutive angles are supplementary. So I would abbreviate again. Consecutive angles supplementary. That one's not quite as much of abbreviations, but when you consider the full length of the word, it kind of is. So if parallelogram, that implies consecutive angles are supplementary. So I'm going to move this on down so we can see the rest of our properties. There we go. Next property says, and it starts out a little bit differently, if a parallelogram has one right angle, then it has blank. So if I look at the quadrilateral that they've given me, and it says that it's a parallelogram, let's say that it has one right angle. So let's give it angle A as a 90-degree angle. Well, what do we know from our previous properties? We know that in a parallelogram, opposite angles are what? Scroll on back up and look. Opposite angles are what? Congruent. So if angle A is 90 degrees, then angle C must also be 90 degrees. You bet. And then I also know from the previous property that if a quadrilateral is a parallelogram, then consecutive angles must be supplementary. Well, what kind of angle measurement would be supplementary with a right angle? 90 plus what equals 180? It would be 90 degrees, right? So angle A plus angle B must equal 180. That means angle B has to be a right angle as well. Same over here with angle D. So if a parallelogram has one right angle, then it has 4 right angles. So let's start out with the hypothesis that we have. If the measure of angle A equals 90 degrees, then the measure of angle B equals 90 degrees. The measure of angle C equals, and you guessed it, the measure of angle D also equals 90 degrees. The shortened version is if parallelogram has one right angle, then it has 4 right angles. Again, doesn't seem like it's much of an abbreviation, but it truly is. All right, we have 2 more properties to discuss about parallelograms, and just take a step back and look at all the things that we've written about parallelograms. You probably knew before that a parallelogram had opposite sides parallel, but you probably didn't know that all of these little properties existed for parallelograms. They're truly a special polygon. The next property says if a quadrilateral is a parallelogram, then its diagonals bisect each other. Now, we've run into this word before. Bisect, oh, there we go. Bisect, this prefix means to, and sect means like sections or to cut. But we're not just cutting this into 2 random length sections. To bisect means to cut into 2 congruent sections, right? To cut into 2 congruent sections. So what this means is that this diagonal right here, drawn from point A to point C, bisects or cuts into 2 congruent segments, segment BD. So that means that BE, that segment is congruent to segment ED. That also means that segment BD is bisecting segment AC. So AE, that segment, is congruent to segment EC. So we have a lot of different stuff going on in this one. This one is usually the one that people forget a little bit about because it's a little different. It doesn't have to do with the sides or the angles. It has to do with the diagonals, which you typically have to draw in a parallelogram. So our conclusion is that segment BE is congruent to what segment? ED. And what's the other pair of congruent segments? Segment AE is congruent to segment EC. Wahoo. If I were going to shorten this for use later in my explanations, I would say if a quadrilateral is a parallelogram, then the diagonals bisect each other. So I would say, I would abbreviate diags, bisect, ooh. And then each other, I don't know if you've seen this abbreviation before, but E/O is a common abbreviation for each other. Not just in math, in general, like life. E/O means each other. And then finally, we have our last property. If a quadrilateral is a parallelogram, then each diagonal divides the parallelogram into 2 congruent triangles. Two congruent triangles. Now, this one is a little bit more difficult to explain if we haven't talked about our triangle unit yet. Typically, in the past, we've already talked about triangles and congruency and how to prove congruence and things like that. But this year, this lesson comes before our talk about triangles. But we can still talk about the congruent triangles that exist here. One of the things that you're going to learn about congruent, corresponding angles and corresponding sides congruent in some triangles. So I notice from our previous properties that this is a parallelogram and that angle A should be congruent to angle what? C, right? Angle A should be congruent to angle C. Now, I'm going to draw over this, and you don't have to draw over this, but I'm going to, and then I'll probably erase it. Remember that we have, in a parallelogram, two sets of parallel lines. So I'm going to draw one set. And then we have basically this transversal right here. You see that? Yeah, so we got that going on. So because we have parallel lines, I'm going to go ahead and draw my proof that these are parallel lines. So because we have parallel lines cut by a transversal, I know from previous lessons that alternate interior angles must be congruent to each other, correct? So that means that angle CBD, this one right here, that angle must be congruent to angle ADB right here. You see that? So if I'm going to talk about congruent triangles here, I need to make sure that I name these in the correct order. So whenever I write triangle, kind of like parallelogram, it has its own figure whenever you name it. So instead of talking about parallelogram A, B, C, D, instead of talking about that, let me go ahead and erase that. Instead of talking about parallelogram A, B, C, D, we're going to talk about the triangles that are within that parallelogram. And when you name a triangle, you just put a triangle, right? So let's name the first triangle. Okay, it doesn't matter what order you name it in. So let's go ahead and name this one right here. Okay, so that triangle right there, we'll call it triangle A, B, D. Is that okay? A, B, D. And it is congruent to the other triangle, but whenever you name the other triangle, you have to name it in a way that has the same vertices in the same order. So for example, and this is where I'm going to erase some stuff because I feel like there's too much going on in this picture for us to understand. So let me erase a little bit of stuff. Bear with me. There we go. Oh, so much better. Okay. So now let's talk about corresponding angles that are congruent to each other. So in the first triangle, the first vertex that we named was point A, right? A. Well, what angle is that congruent to in the other triangle? Well, it's congruent to angle C, which means that angle C needs to be the first vertex that we write in that second triangle. Does that make sense? We need to make sure that they're in the same place in the name as they are in the diagrams. Now, we move to different color. The second vertex that we named was B. B was up here. Notice that in that first triangle, it didn't have any one like angle A, it didn't have two like angle D, it didn't have any, it had nothing. So in this other second triangle, which other vertex created an angle with no arc marks? That'd be angle D. So D is the second vertex that goes in that name. And finally, angle D in our first, that's right here. There were two arc marks. What also has two arc marks in the second triangle? What's the angle created by vertex B? Do you see those? Them so that the corresponding parts of the congruent triangles are in the same place in the name. So we do have two congruent triangles here. So the shortened version of this is if a quadrilateral is, oh, I don't want that color, sorry. If a quadrilateral is a parallelogram, then each diagonal bisects the parallelogram in two congruent triangles. Basically just a whole bunch of symbols thrown in there in substitution for the words. Okay, so we have spent roughly 20 minutes talking about these properties, and I am not feeling bad about that because I really think it's important that you understand these properties. Parallelograms are really cool. They have a lot going on for them that are always true as long as you have the parallelogram. So I'm going to slide down to example 1. Example 1 says ABCD is a parallelogram. So quadrilateral ABCD is a parallelogram. Before you read on, go mark that this is a parallelogram. So I'm going to mark parallel segments here. I'm going to mark parallel segments here. Go mark that it's a parallelogram as soon as you know it. Okay? It says find each measure and state the theorem or definition that supports your answer. So the first thing we have to do is find the length of segment AD, and then we have to find the measure of angle B. So we've got to find a length of a segment, and then we have to find an angle measure. So in the length of the segment AD, that's this right here. This is what I need to find. That has a measure of 7x. Well, go back to your properties. I'm not going to, but you can. Go back to your properties and try to find something that has to do with sides of a parallelogram. We already know by definition that the sides are parallel to each other as long as they're opposites. But what else do we know about the sides of a parallelogram? Well, we know from the very first property that we discussed that opposite sides of a parallelogram are congruent to each other. So I can set up an equation if the sides are congruent, saying that the measures are equal to each other. So I would say that the length from B to C, which is 5x plus 19, is equal to the length from A to D, which is 7x. And the reasoning is because if parallelogram, then, because remember we have to prove or state a theorem definition that supports our answer. So the reason I can set up this equation is because if the quadrilateral is a parallelogram, then opposite sides are congruent. Now, isn't that better than writing the entire paragraph? The answer is yes, it's definitely better. So I need to solve for x because I'm supposed to figure out what the length from A to D is. So I'd like for you to pause your video, solve for x, and write with the answer what the length from A to D is. Pause. Okay. You should have been able to show that the value of x is a fraction. It's 19 halves. And when you substitute 19 halves into the expression for side length AD, then you're going to get 7 times 19 halves, which is 133 halves. And you don't have a unit of measurement, so you just label it as units. So what I'd like for you to do is look at part B. You're supposed to find the measure of angle B. So I'm going to go circle the measure of angle B. That's right here. That's what I'm finding. And you only have one other angle measurement given to you. You need to decide if it's the consecutive angle or an alternate angle. I'm sorry, consecutive angle or opposite angle. You need to go find a property that matches that and try to set up an equation. So pause your video and try part B. Check back when you have an answer. Okay. Hopefully you determined that angle B and angle A are consecutive angles. The property that talks about consecutive angles in a parallelogram states that if a quadrilateral is a parallelogram, then consecutive angles are supplementary, which means I was able to add the measure of angle B plus the measure of angle A and equal it to 180 degrees. You get 11 for the y value, which you then must substitute back into the measure of angle B's expression to get 71 degrees for that angle measure. Okay. So I'm going to scroll down to example. It says that quadrilateral WXYZ, and I know it's a quadrilateral because there's 4 points, 4 vertices, which means there are 4 sides, so it must be a quadrilateral. Just filling in how I know that. So quadrilateral WXYZ is a parallelogram. So I'm going to go mark my parallelograms. I'm not going to fill in those arrows though, because it takes time. Find the measure of angle W. So this is what I'm finding. State the theorem or definition that supports your answer. So I need the measure of angle W. I need to state the theorem or definition that supports my answer. I can't just throw an equation down there and say, hey, this is my answer. I need to have support, kind of like if we're doing a proof. So I noticed that angle W's measure is as an expression in the diagram, but I also noticed that there is an expression for the opposite angle. And if I scroll up to the properties, I can read that if a quadrilateral is a parallelogram, then opposite angles must be what to each other? They must be congruent. So if you know the angle W and angle Y's measures are congruent, or sorry, the angles are congruent, then we know their measures must be what? Their measures must be equal. So take a moment to set up your equation, put your theorem that tells us why, the shortened version please, and go ahead and solve for the measure of angle W. Pause your video. Okay, you should have been able to set those angle measures equal to each other since the opposite angles in a parallelogram are congruent. I've given the theorem beside it. If quadrilateral is parallelogram, that implies opposite angles are congruent. If I add 5n to both sides and add 2 to both sides, I get an n value of 18, which when substituted into the expression for the measure of angle W, you get 106 degrees. Okay. So I'm going to go to example 3. Example 3 is a little bit more difficult. Notice that instead of having just the sides, it also has drawn the what? What are those things that are extra? It has the diagonals, right? It says find the values of x and y. So that's what I need, x and y. In the parallelogram, so this is a parallelogram, all of my properties from the first page of notes apply. Let me go ahead and draw my parallelogram stuff. State the theorem or definition that supports your answer. So we've got to give a reason. We can't just throw stuff on our paper. And the only thing that's labeled here is the diagonals. I don't have any side measurements that are labeled. I don't have any angle measurements that are labeled. And so I need to go back to my properties that have to do with diagonals. Now there are 2 of them. The first one says that if a quadrilateral is a parallelogram, then its diagonals bisect each other. So that seems like it could be kind of useful. The second one says that each diagonal divides the parallelogram into 2 congruent triangles. Now, I'm not sure how helpful it would be to divide into 2 congruent triangles. However, I am going to use the one that has the bisecting of each other. So I can go ahead and say that this segment and this segment are congruent. So y is equal to x plus 3. I can also say that this segment and this segment are congruent to each other. So y plus 7 equals 3x. I can write these because if parallel, then diagonals bisect each other. And a lot of times geometry students freeze here and they're like, what in the world do I do? Well, recall back from your Algebra 1 and Algebra 2 days, if you have 2 equations with 2 variables, 2 unknowns, then this is a system of linear equations. And you can either use substitution or elimination to solve. Right now, this is set up for substitution. So we're going to take x plus 3, and since it equals y, we're going to substitute it for y. I'm going to pause my video, finish working the problem. You need to do the same, and then check back for the answer. All right, folks, hopefully you were able to find the value of x first. You would have gotten a value of 5, and if you substituted that into either of the equations in the system, you would come up with an additional y value of 8. And that's what I was asked to find. So finally, I'm going to move down to example 4. It says 3 vertices of parallelogram JKLM are, and then it gives them to you. So take a moment to plot your vertices. J is at 3, -8. K is at -2, 2. L is at 2, 6. And then M is the one that we don't know. But if you don't know now, or up until now, whenever you name a parallelogram, your vertices must go in order. So I'm going from, and I'm not going to use my straight edge tool because I don't want to. But if I have parallelogram JKLM, then I have to start at J. It goes to K. It goes to L. And then M must be floating somewhere around here because that must be where the last vertex is, so that we have this parallelogram. So there are a couple different ways that you can get vertex M. This is what I want, and then I want to state the theorem or definition that helps me. Most recently, we've talked about slope of parallel lines, and we know that the sides, the opposite sides of parallelograms are parallel, so they should have the same slope on a graph. And so in the past, what students have done is they've found the slopes of the segments that are there, and they've mimicked those to find missing points. So that's what we're going to do today. I'm going to do it in red so maybe it stands out a little bit more. So from K to L, my rise is 1, 2, 3, 4. My run is 1, 2, 3, 4. So I must go up 1, 2, 3, 4 and over 1, 2, 3, 4. I also need to make sure that the other segment is parallel. So if I find the slope, it is a rise down of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And over 1, 2, 3, 4, 5. So I'm going to do the same thing from L to this hopeful point M over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. This must be point M. So point M's coordinates are 1, 2, 3, 4, 5, 6, 7, comma, -4. And my reasoning would be that if a quadrilateral is a parallelogram, that implies, by definition, that opposite sides are parallel. So the very last thing that we have is the properties of the parallelogram. This is for you to fill in. I'm not going to fill it in for you, but you need to take the properties from the first page and summarize them in all of these boxes. So you've got 7 boxes, you've got 6 properties plus the definition at the top of your notes for parallelograms. So take some time to fill in that summary so that you have a quick reference, and you'll have a great day.